Have you ever wondered what makes up everything around you, from the air you breathe to the screen you're looking at right now? The answer to this mystery lies in a world too small to see with the naked eye, a world of atoms. Atoms, you ask? Yes, indeed. These tiny particles are the building blocks of everything in the universe. They are so minute that millions of them could fit on the head of a pin. But despite their tiny size, they hold the power to create all matter. Imagine this. A single drop of water contains more atoms than there are stars in the observable universe. Astounding, isn't it? Atoms are not just in the physical things around us, but also in the air we breathe, the food we eat, and even in the thoughts we think. Yes, you heard it right. Atoms are everywhere, in you, in me, and in every single thing you see or touch. So now you may be asking, what exactly is an atom? Well, let's delve into that fascinating world. An atom, in its simplest definition, is the smallest unit of a chemical element that retains the properties of that element. Imagine an atom as a microcosm of our solar system. At the center of this microcosm is a cluster of particles known as the nucleus. Now, this nucleus is not just a simple blob. It's composed of two main types of particles, protons and neutrons. Protons, they're the positive ones, the cheerleaders of the atomic world. They carry a positive electrical charge. Neutrons, on the other hand, are the neutral peacekeepers. They carry no charge. Both protons and neutrons hang out in the nucleus, creating a positive charge at the center of the atom. But wait, there's more. Orbiting around this positively charged nucleus, much like planets around the sun, are tiny particles called electrons. Now, electrons are the rebels of this atomic universe. They carry a negative charge, counterbalancing the positive charge of the nucleus. The number of electrons in an atom usually equals the number of protons, creating a balance of charges. However, there can be exceptions, but we'll get to that later. Now, you might ask, how do these particles stay in their places? Well, it's all thanks to the forces of attraction. The protons and neutrons, despite their differences, are held together by the strong nuclear force, one of the strongest forces in nature. Meanwhile, the electrons are kept in their orbits by the electromagnetic force between them and the protons. It's a delicate balance, a dance of particles, if you will, that forms the structure of an atom. So, to wrap it up, an atom consists of a nucleus made up of protons and neutrons, with electrons orbiting around it. The charges of these particles and the forces between them keep everything in check. In essence, an atom is like a tiny solar system with electrons orbiting around a nucleus made of protons and neutrons. Now, let's delve deeper into the atom's identity. Every atom has a distinct character, a unique identity if you will, and this is determined by two key numbers, the atomic number and the atomic mass. These aren't just random figures, mind you. They tell us fundamental truths about the atom in question. So, what is the atomic number? It's the number of protons in an atom's nucleus. This is the atom's ID card, the thing that makes it what it is. For example, if an atom has 1 proton, it's hydrogen. If it has 6, it's carbon. If it has 92, it's uranium. Yes, it's that simple. The atomic number is what distinguishes one element from another. Now, onto atomic mass. While the atomic number is all about protons, atomic mass considers both protons and neutrons, the particles that together form the nucleus of an atom. If you're wondering about electrons, well, they're so light that they barely tip the scale, so we leave them out of this calculation. Here's how we calculate atomic mass. We add up the number of protons and neutrons in an atom. For example, if an atom has 6 protons and 6 neutrons, its atomic mass is 12. Simple, right? But there's a catch. Not all atoms of an element have the same number of neutrons. These versions of an element, with the same number of protons but different numbers of neutrons, are called isotopes. Because of these isotopes, the atomic mass we usually refer to is an average, based on the masses of the different isotopes and how common they are. So the atomic number and atomic mass are like the name and weight of an atom. They tell us what the atom is and give us a sense of its size. And just like our names and weights, these numbers are crucial to the atom's identity. Every atom has its own unique atomic number, just like we all have our own unique fingerprints. But wait, atoms have more to their identity than just atomic number and mass. You see, atoms are like chameleons, constantly changing and adapting. Two of the most intriguing forms they take are isotopes and ions. Let's start with isotopes. Isotopes are versions of the same element that have different numbers of neutrons. Think of them as siblings. They have the same parent. The atomic number, which is the number of protons, but they differ in weight, the number of neutrons. For instance, Carbon, the building block of life, has 3 naturally occurring isotopes: carbon-12, carbon-13, and carbon-14. They all have 6 protons, as all carbon atoms do, but they have 6, 7, and 8 neutrons respectively. Isn't that fascinating? Now let's talk about ions. Ions are atoms that have gained or lost electrons. When an atom loses an electron, it becomes a positively charged ion, or a cation. On the other hand, when an atom gains an electron, it becomes a negatively charged ion, or an anion. This gain or loss creates an imbalance between the number of protons and electrons, resulting in a charged atom. Let's take sodium as an example. Sodium atoms typically lose an electron to achieve a stable electron configuration, becoming a sodium ion with a positive charge. Conversely, chlorine atoms typically gain an electron, becoming a chloride ion with a negative charge. These positive and negative ions then attract each other, forming compounds like sodium chloride, which, as you may know, is common table salt. So you see, atoms are far more dynamic and interesting than they seem at first glance. They change their number of neutrons to become isotopes, and gain or lose electrons to become ions. They are not just static entities, they can change and transform, giving rise to isotopes and ions. These atomic variations play a vital role in the diversity and complexity of the material world around us. So we've learned what atoms are, but why should we care? Well, let's dive right into it. Atoms, these tiny particles, are the building blocks of everything around us. They are not just abstract scientific concepts, they are real, and have a profound impact on our lives. Let's start with chemistry. The entire field is based on the interactions between atoms. Chemical reactions are nothing more than atoms swapping partners or changing their arrangements. Understanding atoms allows chemists to predict and control these reactions, leading to the creation of new substances and materials. Next, let's consider physics. Atoms are the playground where the fundamental forces of nature show their might. The attraction between protons and electrons, the strong nuclear force holding the nucleus together, these are all interactions at the atomic level. Grasping these concepts is crucial for physicists to understand the universe's workings and develop technologies from nuclear power to quantum computers. But atoms are not just in the realm of physical sciences. In biology, atoms come together to form molecules, which in turn form cells, the basic units of life. The DNA in our cells, the oxygen we breathe, the glucose that provides us energy, all are made of atoms. Understanding atoms, therefore, is key to unraveling the secrets of life and developing treatments for diseases. In technology, atoms play a crucial role too. Semiconductors, the heart of our digital world, work based on the properties of atoms and their interactions. The future of technology, from nanotechnology to quantum computing, hinges on our understanding of atoms. In short, atoms are everywhere, in everything, doing everything. Understanding them is like having a backstage pass to the universe, allowing us to peek behind the curtain and see how the magic happens. From the food we eat to the air we breathe, from the medicines we take to the technologies we use, atoms are fundamental. So, to wrap it up, let's revisit what we learned today. We kicked off with the enigmatic atom, the smallest unit of matter that retains all the properties of an element. It's like a microcosm of the universe, with its own sun, the nucleus and planets, the electrons revolving in their orbits. We then explored the structure of an atom, understanding how protons, neutrons, and electrons come together to form this tiny, yet incredibly significant entity. We learned about atomic numbers and atomic mass, which are like ID cards for an atom, helping us identify what element it belongs to. Next, we delved into the world of isotopes and ions, variations of atoms that play crucial roles in everything from radioactivity to our body's physiology. And finally, we appreciated how atoms, in all their various forms and combinations, are the building blocks of life and everything around us. Remember, every single thing in this universe, including us, is made up of these tiny, incredible atoms. Keep wondering, keep questioning, and keep learning.